Our last section in level 48 is about vapor pressure. A familiar example of a change of state occurs when a liquid evaporates from an open container. This is clear evidence that the molecules of a liquid can escape the liquid surface and form a gas. We call this vaporization or evaporation. This is an endothermic process because the energy is required to overcome the strong intermolecular forces in the liquid. So they need energy to be able to break those intermolecular forces and break out of the liquid. Alright? The energy required to vaporize 1 mole of a liquid at a pressure of 1 atmosphere is called the heat of vaporization, or enthalpy of vaporization, and I call it the delta H vap because that's what it looks like. Vapor pressure happens when a liquid is placed in a closed container. It's actually more apparent. The amount of liquid at first decreases, but eventually becomes constant. The decrease occurs because there's an initial net transfer of molecules from liquid to vapor phase. So we can see this in a closed-up water bottle that's been sitting for a while, right? The evaporation process occurs at a constant rate based on temperature, but then the reverse process, which we call condensation, is different because it depends on the number of vapor molecules. So in a closed water bottle setting, the condensation that's at the top of the water bottle, if you come back and look at it in a couple hours, would be from the molecules escaping from the liquid and turning into a vapor, but then condensing back down into a liquid to get a sort of equilibrium inside the bottle. So eventually enough vapor molecules are present above the liquid so that the rate of condensation is equal to the rate of evaporation. So at this point, no net change occurs anymore, but the processes are still happening. And so this tells us that this system is at equilibrium. Note that this system is highly dynamic, so that means that the molecules are constantly moving and escaping from and entering into the liquid phase at a high rate. But there's just no net change because the processes are balanced out. So it's still happening even though you can't see it. So these pictures are on page 483 in your textbook. A is showing us how initially evaporation will occur from the liquid into a vapor phase. So the amount of liquid will decrease because the molecules are leaving the liquid phase. But then B is showing us that as the number of the vapor molecules increases, the return rate to the liquid, the condensation, will also increase until the rate of condensation equals the rate of evaporation. And then the system is at equilibrium, where it's constantly going, but there's no net change anymore. The pressure of the vapor present at equilibrium is called the equilibrium vapor pressure, or the vapor pressure of the liquid. This picture shows how you can have vapor pressure due to the atmosphere using a barometer, where in the B picture to the right there's 3 liquids, water, ethanol, and diethyl ether, that have quite different vapor pressures. And the diethyl ether, is the most volatile of the 3, which means that it has the most pressure. And it might be kind of hard for you to see right here, but it is on your textbooks in 484. There is a slight bit of each of the liquids that is still in liquid form above the mercury in these barometers. Liquids with a high vapor pressure are said to be volatile, where the vapor pressure is determined by the intermolecular forces in the liquid. So vapor pressure increases significantly with temperature. So how strong are those intermolecular forces holding it together? So to calculate vapor pressure, we have these 2 equations. We are actually going to use the bottom equation in the example 4. So make sure that you write this down. But a couple things to note. The ln is the natural log. So you have to find that on your calculator for the natural log function. The PVAP is the pressure of vapor at the vaporization, or it's the vapor pressure. Okay. The delta HVAP is our enthalpy of vaporization. R is a different constant than normal. R, instead of what we used back when we did gas laws, we have a new R. It's 8.3145 joules per Kelvin mole. So it's a new constant. It's the same letter. I was not the one who picked these letters. Okay. Temperature also has to be in Kelvin. So if you're given it in Celsius, you're going to have to convert to Kelvin with 273.15. Okay, so we're going to use the second equation for example 4. For example 4, the vapor pressure of water is 25 degrees Celsius at 23.8 torr, and the heat of vaporization of water at 25 degrees Celsius is 43.9 kilojoules per mole. Calculate the vapor pressure of water at 50 degrees Celsius. We are using the second equation from before the previous slide because we have two temperatures that we're dealing with here, and we are given one pressure and we got to find another pressure so let's figure out all the information we have, right? So we know our first temperature given, so I'm going to call it T1 for now, is our 25 degrees Celsius. Well, we need all of our temperatures in Kelvin, so add 273.15 to that and you get 298.15 K Kelvin. Okay. We know that the vapor pressure at the 23.8 torr, or at 25 degrees Celsius, is the 23.8 torr. So I'm going to say the pressure at 25 is our 23.8 torr. Okay. Then we know the heat of vaporization of water, so the HVAP, the delta HVAP, is 43.9 kilojoules per mole. And we are not told this, but we also know that R, our constant, is 8.3145 joules per Kelvin mole. And we want to know the pressure, the vapor pressure at 50 degrees Celsius. So that means our T2, our second temperature, is the 50 degrees Celsius, which, changing it to Kelvin, adding 273.15, is 323.15 Kelvin. That's it. Okay? So, we're going to go ahead and plug into that second equation and solve. Okay? So, we have the natural log of pressure 1 over pressure 2. I'm going to say the 25 degrees Celsius is the pressure 1, or the temperature, the 1s, and then the 50s are the 2s. Okay? So I'm going to go ahead and put my 23.8 over P2, where P2 is equal to the P50, okay, what we're solving for. And that's equal to the delta HVAP over R. Well, we can't just plug those in as they are, because the delta HVAP is in kilojoules and the R is in joules. So they're not going to cancel each other out. We need to convert one of them to be like the other. So I'm going to go ahead and convert the kilojoules into joules by multiplying by 1,000 to get that to be 43,900 joules per mole for the delta HVAP. Okay? So then that way the joules unit will cancel away. So we'll have the 43,900 over R 8.3145 times, and then it's the inverse of the temperatures, but we have to take the T50 first and then the T25 second. But we're going to use the Kelvin numbers. So it's going to be 1 over 323.15 minus 1 over 298.15. Okay, so I'm going to go ahead and solve for the entire right side of the equation. So doing that and simplifying, we have kind of separating out here. Okay, so the ln of 23.8 over P2 or P50, whatever you'd like to put, is equal to, and when you solve that out, make sure that order of operations when you type in the calculator is key, okay? But I got that to be negative 1.37. Well, in order to get the P2, the second pressure, solved for, we have to get rid of the natural log, the ln. So the inverse of the natural log is the e to the x function. Okay, hopefully you've seen this in math class before. So we're going to take both sides, and I'm saying e to the caret. So we do that in order to cancel out the ln. So we'll be left with 23.8 over P2 is equal to, and then in your calculator you have to find that e to the x function button, which on my calculators in the room, it's the second function of the ln button, where you would type in your number first, the 1.37 negative, and then hit second e to the x, and you get, when you do that, excuse me, you get 0.2541, and that's just a little rounding, so I don't have to write out the whole number. Okay? Now it's just simple algebra to get P2 by itself. So we have to multiply both sides by P2 so that the P2's cancel. And then we're going to have to divide by the 0.2541. So P2 is equal to 93.7. And since it's pressure, we look back at the problem and see what the other pressure unit was, and it was torr, so we're going to label that as torr. If it was atmospheres, we label it atmospheres. You just look at what the other pressure was. To finish up level 48, you're supposed to read pages 488 to 490 about the vocabulary associated with changes of state, so all of that stuff may be fair game on the quizzes and on the test, so make sure you look over that information. Alright, this is the end of 48. Please check your checklist to know what to do next.